Welcome to Topic 503. Case Studies in Ecosystem-Based Urban Planning, developed within the EPD-Net project. Filling the Gap, Ecological Planning and Design Learning Network and Adaptive Smart Training Module for Disaster-Resilient and Sustainable Cities. Today, we will examine 3 international case studies that demonstrate how ecological knowledge, natural capital, and planning tools can be integrated into urban development. These cases, Portland, Curitiba, and Jiaxing, represent different contexts and models, yet all illustrate the transformative potential of ecosystem-based approaches. Our first case is Portland, Oregon. Portland's Natural Resource Inventory is a systematic, citywide assessment that maps ecologically significant resources. The inventory serves as a regulatory and planning tool. By identifying high-value ecological areas, the city integrates these layers directly into zoning decisions, development permits, and long-term growth strategies. Ecological data is treated as essential planning infrastructure, just like transportation or housing. The methodology relies heavily on geographic information system data and maps of natural features such as rivers, wetlands, flood areas, and vegetation. GIS models were developed to evaluate and rank the relative ecological importance and health of these natural features. They evaluate features based on various scientific and ecological criteria, like proximity to water, the type of vegetation present, connectivity between habitat patches, and other ecological functions. The result is a set of GIS-based maps that highlight areas with high ecological value versus those that are more degraded or less functional. These maps enable city planners and resource managers to understand which areas are most critical for conservation or restoration. The inventory also includes lists of species and areas of particular ecological concern. Special habitat areas are areas identified as having high ecological value or containing rare, threatened, or significant species or habitats. The inventory provides maps of these areas to help prioritize protection and management efforts. Fieldwork involves on-the-ground verification to confirm and refine the mapped boundaries and features of wetlands and riparian areas. This process helps ensure that the GIS models accurately reflect current conditions and actual resource extents, reducing errors that might arise from purely remote sensing data. The development and refinement of the GIS models involved a technical review process where scientific criteria and modeling approaches were closely examined by experts. This review ensures that the methodologies align with both scientific standards and local conditions. GIS models produce relative quality ranks for riparian corridors and wildlife habitat areas, based on the number and distribution of various ecological functions they perform. These ranks do not measure absolute resource quality but allow for comparison within the city. The significance of resources is assessed through the functional scores derived from the GIS models and criteria that evaluate ecological functions like stream flow moderation, bank stabilization, and wildlife connectivity. The Natural Resource Inventory is solely for informational purposes. It does not propose specific programs or regulatory actions but provides a comprehensive dataset to inform a wide range of activities related to resource management. The inventory can be used for multiple purposes, including guiding land use decisions, restoration priorities, and conservation efforts, though it does not automatically replace existing inventories used for regulation or policy. The Bureau of Planning makes draft updated maps and reports available to key stakeholders, including city bureaus, regional agencies, organizations, neighborhood groups, and citizens. Stakeholders review the materials and provide feedback based on current ground conditions. The work plan also aligns with efforts to update land use regulations and policies, such as zoning, to support watershed health, possibly through citywide or area-specific initiatives. The process involves collaboration with other bureaus, agencies, and stakeholders, and the ultimate goal is to incorporate the inventory into the city's broader environmental programs. In our second case assessment, we will examine the sustainable planning of the Brazilian city of Curitiba, widely recognized as one of the world's greenest urban centers. The city's planning history extends across several centuries, evolving from an organically developed settlement into an internationally celebrated model of sustainable urbanism. This transformation was driven largely by the major planning shift that began in the 1960s. The earliest formal plans for Curitiba focused mainly on establishing basic urban structure. Pierre Tallois's proposal introduced an orthogonal grid intended to support the development of sanitation infrastructure. However, it did not significantly change the city's spatial configuration or influence its growth trajectory. Following this, the Agache Plan emerged as Curitiba's first comprehensive urban plan. Developed by French urbanist Alfred Agache, the plan aimed to address the city's recurring flood problems, designate a central business district encircled by concentric residential zones, establish land-use zoning regulations, and guide future growth through a radial road network. Although most of Agache's proposals remained unrealized due to financial limitations, aside from the creation of the radial avenues, the plan succeeded in raising public and institutional awareness about the importance of urban planning in addressing growth-related challenges. Curitiba's global reputation ultimately derives from the implementation of the visionary master plan and the creative strategies championed under the leadership of Jaime Lerner, who served 3 terms as mayor between 1971 and 1992. His tenure marked the beginning of a period of ambitious, integrated, and sustainable urban transformation that continues to define Curitiba's identity today. Jaime Lerner played a pivotal role in shaping Curitiba's trajectory toward sustainable development through his visionary leadership, innovative urban planning, and commitment to integrated solutions. During his 3 terms as mayor, the city underwent a remarkable period of transformation. Instead of relying on large engineered structures, he turned to natural processes. A cornerstone of Lerner's sustainable development legacy is the city's integrated public transportation system, especially the bus rapid transit system. He prioritized efficient and affordable mass transit to reduce dependence on private cars, lower emissions, and ease congestion. His leadership also supported the expansion of green infrastructure, including extensive parks, urban forests, and the Green Line project, a biodiversity corridor and linear park designed to enhance ecological resilience and promote biodiversity within the city. Lerner further introduced the concept of urban acupuncture, inspired by traditional Chinese medicine. This approach consists of small-scale, targeted interventions, quick, low-cost projects intended to spark broader urban revitalization. He used urban acupuncture to revitalize degraded areas and improve neighborhoods needing immediate attention. Lerner also promoted waste recycling, environmental education, and the protection of natural areas. His concept of strange archaeology added another dimension to his planning philosophy. This idea centers on understanding and leveraging a city's historical and ecological patterns, its old roads, former streetcar routes, natural land features, and the physical and social traces that have guided its growth. Taken together, Lerner's policies and programs reflected a holistic understanding of urban sustainability that interconnected ecological, social, and economic dimensions. His leadership positioned Curitiba as a global pioneer in sustainable urban development and continues to serve as an influential reference for cities around the world. In this part of the lecture, we will discuss Curitiba's green infrastructure. The goal of this network is to strengthen ecological resilience, support biodiversity, regulate the climate, and improve overall quality of life. All components of the system work together. They form an integrated strategy for sustainable urban development. Curitiba's first major element is its system of extensive parks and urban forests. Together, they cover about 20% of the municipal area. These spaces function as biodiversity hotspots. They also offer recreation and act as ecological buffers. They help reduce urban heat islands and manage flooding. A second component is the network of linear parks and biodiversity corridors. These parks follow the city's watercourses and often connect major ecological zones. These corridors restore degraded habitats. They improve air quality, regulate temperature, and strengthen flood control. Curitiba also addresses flooding through nature-based solutions. Instead of relying only on hard engineering, the city transformed flood-prone areas into parks and lakes. These interventions restore natural hydrological cycles. They reduce flood risks and create valuable public spaces. The city has also invested heavily in vegetation and tree planting campaigns. These programs focus on native species and urban forestation. They help improve air quality. They also provide shade, enhance the visual character of the city, and build civic pride. Tree planting activities promote environmental awareness among residents. Another key element is the system of protected natural and cultural heritage areas. Curitiba maintains conservation units and heritage reserves. These areas protect native flora and fauna. They also serve as important places for environmental education. Green infrastructure in Curitiba is supported by urban planning policies. The Green Plan and municipal legislation offer clear guidance. They include incentives for green development. They also include rules for biodiversity protection and programs for environmental education. These policies encourage both residents and developers to adopt sustainable practices. Finally, Curitiba emphasizes community engagement and education. Residents play an active role in tree planting, park maintenance, and environmental campaigns. Their participation reinforces the understanding of green infrastructure as a shared public resource. Now we will outline the key strategies that shape Curitiba's green infrastructure. These strategies guide how the city protects its ecosystems and improves urban resilience. The first strategy is the preservation of natural hydrological cycles. Curitiba works to restore rivers and water bodies. This approach strengthens flood control and improves water quality. It also brings natural processes back into the urban landscape. A second strategy is multifunctionality. Green spaces in the city are designed to serve many purposes at once. They provide ecological benefits. They offer recreational opportunities. They support education. They also enhance the aesthetic character of the city. A third strategy is the use of cost-effective and low-cost solutions. Curitiba addresses challenges like flooding and heat islands through natural systems rather than expensive engineered infrastructure. Another important strategy is biodiversity conservation. The city protects native species and develops ecological corridors. These corridors support urban wildlife and maintain habitat connectivity. Curitiba also emphasizes integration with urban mobility and land use. Green spaces are connected to transportation networks and residential areas. This supports walkability and cycling. It encourages frequent community use of parks and corridors. In essence, these strategies show how Curitiba's green infrastructure operates as a holistic and multifunctional system. Developing sustainable development strategies is widely understood as a powerful way to improve ecosystem quality and increase the benefits that ecosystems provide to society. Cities with medium or low levels of development often carry a heavier ecological responsibility within regional development, and this responsibility can sometimes place real limits on their economic growth. It is in this context that the study turns its focus to Jiaxing City in China. Using Jiaxing as a case study, the research proposes a methodological framework intended to guide future land use development strategies. The goal is to support a planning approach that balances ecological protection with urban growth, ensuring both environmental integrity and long-term economic sustainability. The study evaluates and compares how different land development strategies may shape land use patterns and ecosystem service values by the year 2035. The motivation for this research comes from the recognition that medium-level cities play a critical role in maintaining both ecological and economic stability at the regional scale. Yet these cities often lack planning strategies that effectively balance development pressures with ecological conservation. By assessing ecosystem service values under several development scenarios, the study seeks to support ecological protection, improve land use efficiency, and promote sustainable urban growth in alignment with regional planning goals. In this study, 8 key ecosystem services were evaluated to understand their contribution to ecological health and human well-being. These services include water conservation, climate regulation, flood mitigation, air purification, soil retention, nutrient recycling, such as nitrogen and phosphorus, carbon storage, and cultural or supporting benefits. To assess these services, the researchers employed a combination of empirical formulas, spatial data analysis, and modeling tools. For each service, they used land cover information, ecological parameters, meteorological data, and environmental variables to quantify the capacity of different ecosystems to provide these benefits. The methodology used in this study is built on a sequence of assessment, simulation, and optimization steps, all centered on ecosystem service values. The researchers began by evaluating the current ecosystem service conditions in Jiaxing City. This was done by mapping the spatial distribution of 8 key ecosystem services, each of which was quantified using specific calculation formulas and model-based methods. To conduct this assessment, the study employed 2 major tools: the Ecosystem Services and Trade-offs Platform Invest and the Intelligent Urban Ecosystem Management System, known as IUEMS. These tools enabled the team to map ecosystem services and compare their performance under current conditions as well as under different future development strategies. The next stage of the methodology involved simulating future land use scenarios. 3 strategies were examined: inertial development, cropland protection, and ecological development. These simulations were produced using the PLUS model. Within PLUS, the Land Expansion Strategy Analysis Model, known as LEAS, played a central role. Using land use data from 2005 and 2020, LEAS calculated the historical probability of land use expansion for different land categories. After completing the land use simulations, the researchers evaluated how the projected changes would influence ecosystem service values in the future. Using IUEMS and INVEST, each ecosystem service was quantified and then translated into an economic value, enabling clear comparisons across all scenarios. The researchers integrated multiple sources of data, including land use and land cover information, meteorological and environmental monitoring data, socio-economic development indicators, and ecological function parameters. This comprehensive dataset allowed for a detailed evaluation of current ecosystem services and facilitated simulations of future land use strategies. The land use cover data were obtained for the years 2005 and 2020 at a spatial resolution of 30 meters. Soil attribute data, such as clay, sand, silt, organic matter, nitrogen, phosphorus, and soil bulk density, were drawn from the Harmonized World Soil Database. Ecosystem type curve number values for different land types were derived from literature sources. Additionally, the digital elevation model data at a 30-meter resolution from Ester GDEMV3 were used to analyze terrain features. The current status of ecosystem service values in the study area indicates a total economic worth of approximately 124.82 billion Chinese yuan in 2020. This assessment highlights the significant contributions of various ecosystem functions, including water conservation, flood mitigation, carbon sequestration, sediment reduction, and pollutant purification. These services collectively support environmental stability and societal well-being, underscoring the importance of maintaining and enhancing ecosystem health to sustain these valuable functions. The driving factors of historical land use change in Jiaxing are primarily influenced by environmental and infrastructural variables. The most significant drivers include temperature, elevation, and proximity to open water, which greatly affected changes in cropland, forestland, wetlands, and grasslands. Specifically, elevation and temperature played crucial roles in cropland and forest dynamics, while proximity to open water predominantly influenced wetland and urban expansion. Additionally, proximity to roads and soil type also contributed to changes in grassland areas, indicating that both climatic conditions and human infrastructure significantly shape land use patterns over time. Under the inertial development strategy, urban expansion accelerates, leading to significant encroachment on cropland and wetlands, with a 44.75% increase in urban construction land and a 17.27% decrease in cropland by 2035. The cropland protection strategy emphasizes safeguarding agricultural land, resulting in moderate changes, but shows limited ecological benefits. The ecological development strategy promotes restoring forests and grasslands, reducing construction land, and expanding high-value ecological areas, thereby enhancing ecosystem services such as water conservation, flood mitigation, and climate regulation. Specifically, the results demonstrate that the ecological development strategy yields the highest ecosystem service values and promotes the expansion of ecologically valuable areas, aligning with urban planning goals for sustainable growth. The model predictions show that implementing such strategies can enhance ecological functions while meeting urban development targets, such as land use area requirements. In sum, the study emphasizes that urban planning can benefit from incorporating ecosystem service assessments, allowing planners to make informed decisions that balance economic development with ecological sustainability. Now we will highlight some comparative insights that emerge when we look across the 3 case studies. Each city approaches ecosystem-based planning differently, yet they all demonstrate the importance of ecological intelligence in urban decision-making. First, the use of ecosystem function mapping significantly enhances planning precision. Second, policy instruments vary widely among the cities. Portland uses zoning, regulatory inventories, and environmental overlays. Curitiba relies on innovative public investment and landscape-based design strategies, such as linear parks and ecological corridors. Jiaxing uses simulation-based planning tools that quantify ecological gains and trade-offs under different land use strategies. Despite their differences, all 3 cases demonstrate that incorporating ecological information early in planning leads to more resilient and adaptive urban systems. They show that when ecosystem functions are recognized, mapped, and integrated into decision-making, cities can better balance growth with ecological integrity. Finally, it is important to note that the long-term effectiveness of ecosystem-based planning depends heavily on continuous monitoring. Long-term monitoring also enables early detection of emerging risks, supports adaptive management, and ensures that policies remain aligned with changing ecological, social, and climatic conditions. To conclude, we can highlight several key takeaways from this topic. First, urbanization continues to intensify land use changes, and these changes place significant pressure on ecological functions. However, we also see that strategic planning, grounded in ecological knowledge, can effectively mitigate many of the negative impacts associated with rapid growth. Second, ecosystem services play a central role in shaping urban resilience. Recognizing these services as fundamental urban assets is essential for long-term sustainability. Third, quantitative evaluation and scenario modeling are essential components of sustainable land management. By using models to test future scenarios, planners can anticipate ecological outcomes and make more informed decisions. Finally, future policies must integrate ecological valuation into fiscal mechanisms and planning instruments. Doing so ensures that ecological assets are not only protected but also enhanced over time. These points remind us that sustainability is not a single intervention but an ongoing commitment to understanding, valuing, and protecting the ecological systems that support urban life.